All right, let's dive in. Have you ever really thought about how a simple, plain sound wave can turn into, well, all the rich and complex sounds we hear every single day? That's exactly what we're exploring today. We're going to get into the world of modulated waveforms, the hidden secret to shaping sound.
Okay, so here's a bit of a riddle for you. What on earth could a vibrating guitar string and a wailing police siren possibly have in common? I know, it sounds like the start of a bad joke, but the answer is actually super cool and gets right to the heart of what we're talking about. They both rely on actively changing or modulating a basic sound wave. Just stick with me and you're going to hear the connection for yourself. So, that connection, the answer is a process called modulation. Seriously, this one idea is the key. It's the fundamental principle behind how sounds are shaped. And what's wild is that once you understand it, you'll start to hear it absolutely everywhere, from your favorite music to the noise on the street. At its core, modulation is actually pretty simple to wrap your head around. You start with a main sound wave, which we call the carrier. Just think of it as a steady, plain tone, like a long beep. Then we bring in a second wave called the modulator, and its only job is to mess with that carrier wave, to change some part of it, like how loud it is or what its pitch is. Let's start with the first type, and it's probably the most intuitive one. It's called amplitude modulation, or just AM for short. And this is all about changing the volume, the intensity of that carrier wave over time. You know, the best way to picture this is to imagine you're listening to a steady tone and you've got your hand on a volume knob. Now just start turning it smoothly and rhythmically up and down, up and down. That pulsing effect you're creating, that's it. That is amplitude modulation in action. And this image right here shows it perfectly. See all those fast, dense squiggles? That's our original carrier wave, the actual rapid vibrations. But that dotted line, that bigger, slower, rolling wave over the top, we call that the envelope. And that's our modulator at work, literally sculpting the overall loudness as time goes on. Now, here's where it gets really interesting. When we modulate the amplitude, we don't just change the volume. We actually create new frequencies that weren't there to begin with. It's pretty wild. As you can see on this graph, you have the original frequency right there in the center, but now you also have two new ones, one on either side. We call those sidebands, and this is what gives the modulated sound its unique character. Okay, so I know this might sound a little abstract, but I guarantee you have heard a very common form of amplitude modulation a million times. It's the phenomenon that musicians call beating. This is such a perfect real-world example. When two guitar strings are almost in tune but just not quite, they create this really distinct wah-wah-wah-wah sound. That wobble, that rhythmic pulse in the volume, that is amplitude modulation. It's literally the sound of two waves interfering with each other. So how does that actually work? Well, it's kind of like a dance between two tones that have slightly different frequencies. As their waves travel through the air, their peaks sometimes line up perfectly, and when they do, they reinforce each other and the sound gets louder. But then they start to drift apart, and eventually, a peak from one wave will meet a valley from the other, and poof, they pretty much cancel each other out into silence. This constant cycle of getting louder and then quieter is that rhythmic pulse we hear as a beat. So we've seen how modulating the amplitude creates a pulse in the volume. Now let's switch gears and explore the second major type. If AM is all about changing the volume, then frequency modulation, yep, FM, is all about changing the pitch. This slide nails the crucial difference right here. With AM, the sound's loudness changes. With FM, the sound's pitch changes. One affects the volume, the other affects the note itself. Simple as that. And just like with AM, you hear FM all the time. That beautiful, shimmering vibrato a violinist or a singer uses on a long note, that's a rapid, subtle frequency modulation. That unmistakable rise and fall of a siren we talked about, that's a really dramatic frequency modulation. Even just the melody of our own voices when we talk relies on it. Now look closely at this waveform. Unlike the AM wave, the height, the amplitude, stays totally constant. What's changing here is the density of the waves. You can see them getting squeezed tightly together, which means a higher frequency or a higher pitch, and then you see them get stretched apart, which is a lower frequency or a lower pitch. So let's look at the frequency spectrum for FM. Remember how AM created just two simple sidebands? Well, FM is a whole different animal. It's way more complex. It generates the original carrier frequency plus a whole series of sidebands. And that complexity is why FM can create such harmonically rich sounds, everything from shimmering bells to harsh metallic textures. Okay, let's put it all together. We're going to look at these two powerful ways of shaping sound side by side to really lock in the difference between them.
This slide is the perfect visual summary. Look on the left with amplitude modulation, you can clearly see the height of the wave changing. That's the volume. And look at its spectrum. It's simple, just the carrier and two sidebands. Now look to the right. With frequency modulation, the height is constant, but the spacing of the wave's changing. That's the pitch. And its spectrum is much more complex, packed with multiple sidebands.
And this table just recaps everything nice and neat. For AM, we're changing the amplitude, or the envelope. We hear it as a tremolo or a beat, and it creates a simple spectrum. For FM, we're changing the instantaneous frequency. We hear that as vibrato or a pitch change, and it creates a much more complex spectrum. Two different methods, two very different sonic results. So the next time you're listening to someone tune a guitar and you hear that beating, or you hear a singer's vibrato on a long note, you'll know exactly what's happening to the sound wave. You're not just hearing a sound anymore. You're hearing its shape being modulated in real time. The real question is, what other sounds will you start to hear differently now?